supposed to chair this session. We have 2 talks before the next coffee break. And the first one will be given by Thomas Vojta of Missouri Science and Technology, and he will tell us about stripes and disorder. Please, the floor is yours.
Okay, thank you very much. And let me also thank you, the organizers, for inviting me. I want to start by recognizing Eduardo's birthday. We have never directly collaborated, but I've nonetheless benefited greatly from his work, because he is a PhD advisor of many people in the room, I understand. And specifically, he was a PhD advisor of Jose Hoyos, who then became my postdoc and has been my longtime collaborator then. So thank you very much for educating Jose. So the topic today is to explore the effects of disorder on systems that shows order, in which the order parameter breaks not just a spin symmetry or a gauge symmetry or something, or a phase symmetry, but also a real space symmetry. For instance, you could imagine but now there's something in the middle. Yeah. So you could imagine thinking about one could imagine thinking about charge stripes, or one could imagine thinking about the nematic order, and then later at lower temperatures, the spin density wave order in the iron pnictides. So what we are going to explore is how disorder, how quench disorder randomness will affect such orders. And here's an outline of what's going to come. So I will first talk a little bit in general terms about symmetry breaking and how different types of disorder interact with order parameters. Then we will look at the minimal model for the physics we are interested in, which is an Ising model with interactions not just between nearest neighbors, but also between next nearest neighbors. And we are going to see that random fields arise generically from spinless impurities in the system, and then the two parts about results. I think I'm losing the battery here. The first is about how such random fields destroy the order, and then the last part is how one can actually bring back the order by manipulating the disorder in this problem. Okay, so there will be Montecolor simulation results in this talk, and this Montecolor work has been done by my former PhD student, Yuxing Ye, and this project is part of my long-time collaboration with Raj, who is there. Okay, so let's get started. Let's think about how disorder will interact with ordered states based on symmetries. So the simplest possible case that one can think of is what people generically call a random mass or random TC disorder. And this is the case when the impurities, the randomness, does not by itself break the order parameter symmetry. So an example for this would be a diluted ferromagnet, where you have vacancies, right, in a picture on the left side. And these vacancies, they don't prefer one of the 2 directions of the magnet, right? The vacancies don't care whether the spins are up or down, so the vacancies do not actually break the order parameter symmetry by itself. However, what they do is they generate a spatial variation in the coupling strengths, which means TC varies from place to place. And that's why we have random TC disorder, right? On the other hand, you could imagine situations in which the order parameter, at which the impurities actually do break the order parameter symmetry. And then we will get a stronger type of disorder that actually competes with the formation of the ordered state itself, right? So if the impurities favor one of the possible symmetry-broken states over another, then they actually compete with the formation of a long-range ordered state in the first place. And so how can random fields arise? Well, of course, we can simply write a random field term in your Hamiltonian, but that's not the question here. Talking about real systems, and one mechanism in how random fields can arise is the case when the order parameter actually breaks a real space symmetry in addition to whatever other symmetry is broken. This would be, for example, the case in such a stripe state. Imagine we have stripe order of some kind, and the stripes could be either vertical or they could be horizontal. Right? So if this is a symmetry that's broken at the phase transition, then it's clear by symmetry that a random arrangement of impurities will generically prefer one of the stripe directions, horizontal or vertical, over the other locally, right? And this is exactly, of course, what random field disorder does. It locally prefers one of the symmetry-broken states over the other. So therefore, random fields are generically expected to arise whenever we have an order parameter that breaks a real space symmetry in addition to a spin or gauge or whatever other symmetry you have. All right. So now let's try to discuss a minimum model where one can see the physics that arises from this setup. And a minimal model can, for instance, be this J1, J2 Ising model in 2 dimensions, which has 2 terms in the Hamiltonian. There is a J1 term that couples the nearest neighbors on the square lattice. And then there's a J2 term that couples the next nearest neighbors, meaning it goes across the diagonal. And depending on what the values of these 2 couplings are, you get different ground state phases. This is actually not very hard to understand. It's clear if J1 is very large and positive, then the system wants to be a ferromagnet, right? It's also clear if J1 is very large and negative, then the system wants to be an antiferromagnet with a staggered orientation of the spins here. The interesting case for our purposes is the case when J2 is actually negative. So we have a negative interaction between across the diagonal, which favors spins to be opposite across the diagonal of the square. And if we make this a dominating term. In this case, the ground state will turn out to be stripe ordered in this way. And it's clear that by symmetry, these stripes can be either horizontal or vertical, that it gives you the same ground state energy. So that will be the starting state for the discussion that's going to come. Okay, so much is known about this model in the, without impurities. This has been studied to a large extent. And here's a phase diagram that summarizes some of the results for the clean model. I'm focusing here on the case where J1, the nearest neighbor interaction, is positive, favoring ferromagnets, and J2 is negative, which will eventually lead us to the stripe phase if it's big enough. Right, and so here at 0 temperature, you can again see the phases I discussed already. Right, for weak J2, we get the ferromagnetic phase, and then for larger J2, when the interaction across the diagonal dominates, we get a stripe state. Right, and then they don't have to be, but they turn out to be. This line is actually very interesting. Hang on a minute, and I'll say a little more about this. So yes, and we can talk about the phase transitions, which have been characterized very well. So there's nothing interesting about this phase transition here. That's a generic Ising phase transition, a 2D Ising universality class. Then we have this transition here, where the 2 phases touch. And following Landau's arguments, this has to be a first-order phase transition because 2 different symmetries are broken. This one is actually interesting, as Vlad pointed out. So it turns out that the transition remains first order here, and then there's a multi-critical point, and then it becomes continuous, but with continuously varying exponents that follow the Ashkin-Teller universality class. So I don't want to talk about this because this is not the main topic of my talk, but there is some interesting physics going on already in the clean case. All right. So that's the starting phase diagram for the clean model, and now we put in this order. And here's how we do this. So here's the Hamiltonian we are actually studying, and we are putting this order in via site dilution, right? So we randomly remove a fraction of the spins, and this is independent randomness. Each site is removed with a probability p, and the epsilons in the Hamiltonian here, they simply encode the plus, the 1 or 0 for the vacancies. All right. So now let's think about what will happen if we do this. And I think for the ferromagnetic phase, not terribly much needs to be said, right? As I already pointed out in the introduction, the order parameter breaks the Ising symmetry. And I'm really losing the battery here, but the vacancies do not. Yes, that's much better. The vacancies do not break the Ising symmetry. Therefore, we get random TC disorder, which means that the ordered phase will survive and the transition temperature will be suppressed a little bit. Yeah, that's essentially all. And of course, there will be a new universality class for the transition, which I'm not going to talk about, at least not at this point, because that's not the main focus of this talk. On the other hand, it's much more interesting for the stripe phase, because this is one of those cases where the order parameter breaks a real space symmetry, in this case, the rotation symmetry of the lattice, right? We can have horizontal or vertical stripes. And the impurity arrangements in general will locally break that symmetry, and therefore we expect a much stronger coupling between the impurities and the stripe order parameter. And this is what's going to form the main part of this talk. Specifically, it turns out that in this simple model, we can actually microscopically understand how the random fields that I was alluding to, how they arise. First, it's clear that a single vacancy, if I just put a single vacancy in my system, of course does not break the symmetry between the two stripe directions, and therefore nothing happens. However, as soon as you put more than one, then the symmetry between the stripe directions can be broken, and it turns out that it's interesting to look at vacancy pairs on nearest neighbor sites. And if you now simply calculate the ground state energy for this plaquette and compared with this plaquette, so this one has horizontal stripes and this one has vertical stripes, right? Then you find that a horizontal vacancy pair prefers horizontal stripes by a certain energy amount, which is 2J1. Correspondingly, a vertical pair of impurities would prefer vertical stripes, right? And that means now we have the random field physics that we were already expecting, right? Depending on what your local impurity arrangement is, you will either locally prefer horizontal stripes or will locally prefer vertical stripes. And one can actually estimate the overall strength of that random field disorder by estimating how many of these nearest neighbor pairs one has in a sample of a given size, right? That's very simple, right? You simply count how many vacancies you have. That's this L squared times 1p, right? L squared times p gives you the vacancy concentration, or number, I should say. And then the other p is simply the probability that you have another vacancy on the neighboring site. So you can estimate the random field strength coming from that mechanism. And this is just a plot confirming this argument. And you see that these numerical results that are obtained by simply calculating the ground state energy for the horizontal configuration and the vertical configuration and compare these two, that this follows this prediction. All right. So that means we have established that we have these random fields. And let me note in passing that, of course, this was a ground state argument. can think about thermal fluctuations, and that's something I'm going to postpone for the conclusions. All right. So now, what does such random field physics do? And as many of you will know, right, this is governed by the Imry-Mar argument, which looks at the possibility of domain formation. Because in the presence of such random field disorder, we have now two competing effects. On the one hand, it may be favorable for the system to align the local stripe direction with what's ever preferred due to the random field disorder. Right? Over here, horizontal stripes, over here, vertical stripes. On the other hand, it's clear that this costs you some energy because you have to form a domain wall between the two phases. The Imry-Mar argument compares the two energy scales. For the gain from the random field, you can make a simple central limit theory-based argument. Right? This is the square root of the volume of a domain. And therefore, if you align this domain with a local random field, this is the typical energy gain that you will have. On the other hand, you have to pay a price because you have to form a domain wall. And the domain wall energy for the discrete symmetry case, yeah, we really have a hard domain wall, can be very simply estimated from the area of the domain wall. All right, and now you can see that if the random field energy wins, right, then domain formation is always favorable, and then the long-range order will be destroyed by domain formation. Whereas in the other case, long-range order can survive, at least if the random field disorder is not too strong. What this simple argument gives is 2 is a marginal dimension. So for dimensions above 2, the long-range order can survive weak random fields. For dimensions below 2, any random field, no matter how weak, will destroy the long-range order by domain formation. And in 2D, the argument is too simple-minded, but people have worked out what happens in 2D, and it turns out that also in 2D, the random field destroys any long-range order. However, because it's a marginal case, the length scale associated with this domain formation becomes very, very large. Meaning, if you have a weak random field, the order will survive over a very, very large length scale before it's finally destroyed. So all of this has been known from the physics of the random field Ising model for a while, and we are now applying this to the problem at hand, right? So let me very briefly talk about how we do the Montecolor simulations. I'm happy to talk about more in the discussions if anybody's interested. So because we have frustration, we cannot use cluster algorithms, so we have to use single spin flip metropolis algorithms. We added the second move class, exchanging the spins across a diagonal. This makes the simulations a little bit faster because it directly turns horizontal into vertical stripes and vertical into horizontal stripes. But it's not a qualitative change, it's still a local move. Because we have to can only use metropolis, the system sizes are only moderately large. We go up to 192 squared. We look at 2 different types of 2 different side dilutions, and then there's a few other parameters. The main observables that we study in order to understand the phase transition are these stripe order parameters. And so what you see here is these are magnetizations, but they pick up this phase factor that depends either on the row or on the column, right? And therefore they pick up on either horizontal stripes or on vertical stripes, right? So this one measures the strength of the horizontal stripe order, this one measures the strength of vertical stripe order, and then we treat this as a 2-component vector order parameter. And we can define a Binder cumulant, so one of the favorite tools Montecolor practitioners use, which is a dimensionless quantity which allows us to find the phase transition by looking for the crossing of different curves. Right. And of course, in particular, because we can only use single flip algorithms, we have to make sure that we equilibrate properly. Equilibration is difficult even without random field disorder and more difficult with random field disorder. So we have been very careful there, which explains small system sizes. But here, I show you representative results comparing 2 Montecolor runs, one from a hot start, so starting from the spins pointing in random direction, and the other one from a cold start, means they start from the perfect stripe order. And you see that within the error bars they agree, which shows you that at least for this example, we have achieved equilibration. All right, so now let's talk about results. And And so here is, just to get you a feel for what's happening, these are just some snapshots of the spin configuration. They are taken at a low temperature, well below the ordering temperature of the clean system. It's essentially very close to zero on the scale of this problem. And you can actually see the domains, right? So here we have a horizontal domain. Here we have a vertical domain and so on. And this can be more easily visualized by replotting the same results, introducing the local pneumatic order parameter, which allows us to locally distinguish between horizontal and vertical stripes. So this simply adds up the bond variables, so the products of neighboring spins, over all the bonds associated with one central site, so all the 4 bonds, counting horizontal bonds with plus and vertical with minus, right? And again, so now here you see the correspondence, right? So these are the horizontal stripes in red, and these are the vertical stripes in blue. So what we are seeing in this example is we have domain formation with a characteristic scale, which is, I don't know, maybe 50 or so, right? And we have as many blue as red sites, which means there's no long-range order. Okay. So now let's look at this more quantitatively. So here is first a plot of the Binder cumulant for this case, and as you can see, there's no crossing. Instead, with increasing system size, the Binder cumulant shifts downwards and to the left, meaning towards the behavior of the non-magnetic phase. So that indicates there's no phase transition, and if you analyze this quantitatively, then you see that the stripe phase, which used to be here, is completely destroyed in this case. In contrast, let me just note in passing that the ferromagnetic phase survives as expected, just with a reduced TC, precisely what one would expect from random mass disorder. Okay, so far this is kind of standard law, right? So the system does exactly what we would have expected. We have identified these random field effects. We have understood that they should lead to domain formation, and this domain formation destroys the long-range order. So now let me talk about what we can do to actually bring the ordered phase back, right? And I'm going to talk about two different mechanisms that may be interesting for controlling this effect. The first one has to do with the spatial distribution of impurities. And remember, I made the point that it's actually impurity pairs that produce the random field physics, not single impurities. And it turns out that at least in this model, this is a rigorous statement at t equals 0. There is literally no random field term if there are no nearest neighbor impurities. Which means by introducing anti-correlations between the impurities, we can weaken the random fields, right? And we can bring back the stripe phase. And that's what we did in an older paper a couple years back. So we introduce perfect anti-correlations, which means we distribute the impurities randomly, but we don't allow configurations that have impurities on nearest neighbors. And that's the only change. And what you can see is that in this case, we now run Montecolor simulations for such a system. We actually do get a crossing of the Binder cumulants, and the resulting phase diagram has a stripe phase, because now we have switched off the random field physics by introducing these perfect anti-correlations. And instead, what's left is just the random TC effect, reducing the coupling strengths coming from the vacancies, which means that the transition into the stripe phase is now at a slightly lower temperature. All right, let me also note in passing, it's not the topic of today's talk, that there's interesting stuff going on here, right? This, in the clean case, this was a first order phase transition. We know this cannot survive in the presence of disorder. So something has to happen, and very likely there's an intervening spin glass phase. And again, this is not the topic for today's talk. So this is the first way of controlling the random field physics in this problem, right? If you have anti-correlations between your impurities, and you can reduce or completely switch off the random field physics, meaning you can break the stripe phase, or you can at least very strongly increase the length scale over which it survives, so that may be big enough that it's effectively infinite for experiments. Now let me talk about the second mechanism, that we can use to control this effect. So imagine we have such a 2D system and we apply strain to the sample, right? Uniaxial strain. Then what that would do is it would actually globally break the symmetry between the horizontal and the vertical couplings, right? So let's see what happens in this case. So in the model, what we are simply going to do is we are going to make the coupling constants J1 dependent on the direction. The horizontal stripes get a J1H and vertical stripes get a J1V, and we parameterize them in this way. And so we have the delta J, which parameterizes the difference between the directions, and that is somehow related to the strain we apply to the sample, right? Okay, now by symmetry, it's again relatively clear what one should expect, right? Now, the symmetry between the two stripe directions is now globally broken, right? And therefore, we would expect that one of the stripe directions will win, which should reduce or diminish or kill the random field physics, right, on long enough length scales, right? And the interesting question is, how does it happen? And particularly, how much of the strain do you need in order to make the random field physics go away, right? Because one could easily imagine experiments where maybe because how you grow your 2D system on a substrate, that there will always be some strain, right? Okay, and so here's already kind of a summary of the results, right, which I will explain in more detail. So these are the same snapshots that I showed you before, which encode the local pneumatic order parameter. And these are different delta J values, right? So delta J varies by 0.02 compared to unity. And then here it gets a little bigger. And what you see is, you see the expected effect, right? So if we make the horizontal stripes bigger, horizontal coupling bigger, right, then the horizontal stripes are more likely than the vertical ones. And therefore, red starts to dominate the graph here. But what's interesting and maybe not entirely obvious is how small a change is actually needed in order to kill the random field physics. Already at 0.2%, right, red is clearly, obviously, much stronger than blue, right? So the J1, J2 Ising model does not have a separate nematic phase. So the phase transitions coincide in this problem, right? All right. So now let's look at this a little more quantitatively. So again, these are in some sense the raw data from the Montecolor simulation that show crossings of binder cumulants. So first of all, the important point is we do see crossings, right? Which we didn't see in the absence of a delta J. We also see that the crossings actually drift, which is expected because at these very small values of delta J, we expect crossover physics, right? But we can extrapolate these crossings to infinite system size and then extract the values. This main panel here shows the results. And the first thing you notice is how steep the curve is close to zero, right? So as we have already seen, the first point here, right, brings you back to a TC scale comparable to that of the clean system. We can actually replot the data. So this was not the extrapolation, which is not shown. I take that back. So this is a replot of the TC data, which we replot as 1 over TC versus the log of delta J. And you clearly see this is a linear dependence, which then means that TC has this very interesting, extremely steep 1 over log delta J dependence. Again, showing that it only takes an extremely small delta J to produce a sizable TC of the comparable to the ones of the clean system. So how can we understand this somewhat unusual dependence? We can understand this by using two pieces of input. The first one has to do with the geometric structure of these domain patterns. which have been studied to some extent, actually in pretty great detail, for the random field Ising problem. Right? When people studied how do these domains look like in the random field Ising model, and what they established is that the domains close to the symmetry point, so in our case close to delta J equals 0, resemble the critical percolation problem. So that's input number 1. And input number 2 is of course, that people have known for a long time now how a simple Ising model on a critical percolation cluster, how it behaves, right? And it is well known that the Ising model on the percolating lattice has this dependence of Tc on the distance from the percolation critical point that is logarithmic. This is only 2D, yes. And this has to do with forming the 1D paths in the critical percolation cluster over which the correlations have to extend. And now combining these two effects, right, we immediately arrive at the logarithmic dependence of the transition temperature on the global symmetry breaking that, again, you may want to associate with strain in your head, have a model of what it could be. All right. Now, we also studied the critical behavior of the emerging transition, right? We have now brought the stripe transition back, and now it's interesting to ask what is its critical behavior, what's the universality class, it's easy to make a guess, right? Since the stripe symmetry, horizontal versus vertical, is already broken, right? We have only an Ising order parameter left. Therefore, we expect the transition to be in the Ising universality class, but the disorder still creates random Tc disorder, so it should be the disordered Ising universality class. And that's actually an interesting universality class because for the Ising model, random Tc disorder is actually marginal with respect to the Harris criterion. Right? D times nu is exactly 2 for the 2D Ising model. And therefore, renormalization group calculations predict that we get the clean Ising exponents by universal logarithmic corrections. And specifically, the specific heat is predicted to have this very interesting double logarithmic dependence, which I've written here as a dependence on the system size, because this is how we're going to study it in Montecolor. And along the same lines, the susceptibility has a leading power law that's governed by the clean Ising exponents, and then a logarithmic correction. Yeah. I think John Cardy did. I can dig it out. Pardon? There are yeah, right. That yes. All right. So it's clear that actually proving this is numerically non-trivial, right? Logarithms are very hard to find numerically, but I think we managed to do this. So let's start with a specific heat. So we are testing this double logarithmic L dependence. And so this is a plot of specific heat versus log L. So which means if it was actually a simple log, like for the normal Ising model, with a clean one, it should be a straight line. But you see the data do not follow a straight line. They are very clearly deviating from the straight line. I should point out the error bars are the little horizontal bars down there, so they're extremely small. And so the double logarithm behavior fits, whereas neither a normal log and the power law fits. So that's a good evidence for this disordered Ising universality class. And then here, in order to confirm this behavior, we actually divided out the leading power law with the Ising exponents. Right? This is divided out here, and then the rest actually shows this logarithmic behavior. Again, very clearly different from a power law. Okay, so I think this is reasonable evidence that indeed the critical behavior does follow this disordered Ising universality class behavior as predicted by the RG. All right, and with this I'm at the end. So let me summarize the take-home messages. Right. So the first important is the general observation that whenever an order parameter breaks a real space symmetry, then we would expect the generic non-magnetic impurities or some other kind of randomness will create not just random TC disorder, which is benign, but a much stronger random field disorder for the order. And in 2 dimensions, at least, these random fields destroy the long-range order by domain formation. But I've shown you two ways how this can be switched off, right? One is has to do with a weak global symmetry breaking, which might appear via strain or some other mechanism, or the effect can also be weakened or completely switched off by impurity correlations. Perfect anti-correlations, at least in this model, will get rid of the random fields effects. And so what that means is that we have now extra new ways of manipulating the phases of the system. Thank you very much.
Thanks for the talk. We have time for questions. Yours.
Thank you. Everything you were saying is classical, right?
Right.
So far. So suppose you switched on a transverse field and looked at a quantum phase transition as you tune some other parameter.
Right.
Do you expect similar, I mean, the 2 transitions to be destroyed and the quantum critical point also wiped away, or?
Right. Yeah. So a lot of the general results or arguments will carry through, right? As you can already see, the Imri-Ma argument does actually not worry about the fluctuations, right? And therefore, it applies in exactly the same way for a thermal transition as it would be for a quantum phase transition. So again, random fields would destroy the long-range ordered phase, and therefore the phase transitions, there would be no difference. What's potentially different is the last part of the talk, when I discussed how the global symmetry breaking via strain or something like this actually brings back the transition, because the arguments that led to the 1/log T behavior, of course, they would be modified if instead we would look at quantum fluctuations instead of thermal fluctuations destroying the order on the percolation cluster. So this dependence of the resulting ordered of the critical parameter of the quantum phase transitions that you want to look at, right? On the delta J, or this would change.
Yeah, so actually something that you said you're not going to talk about, but let me still ask. Because we've studied a model, like if you take Coulomb interactions on the lat, it's very similar, and because it's very frustrating, then you can get stripes as the ground state. And but what we always found is that in this case, or not always, but when the lattices are frustrated enough, then the transition happens to be first order, if you can crank up the frustration enough. So I was wondering, I always wondered, why is it that if the frustration is stronger and stronger, then the transition somehow becomes first order? So is there some understanding that you have of this? Because I don't, and I'm curious.
But I don't. This is not a rigorous statement, right? Because even in this simple model, in the clean case, right? One could argue that the frustration is strongest up here, right? When J2 is 1, and there the transition is actually second order. Right. So, you mean here? Yes. Right. Right. Yeah. No. So I don't think so. I don't think I have a general understanding of why this transition wants to be first order. Beyond the calculation, I don't have a good argument.
Raphael.
So Thomas, if I take the random field Ising model, right, and now I start shifting I also include a uniform field. Then, if I remember correctly, you need a critical value of the field, I think it's 0.00375, to go a first order transition from the domain breakup to long range order. What you're seeing is a completely different physics, right? Because you say that even infinitesimal symmetry breaking field, uniform field, will lead to long range order. Is that correct, or am I misinterpreting?
I think it may depend on what precise question you ask, right? So, do you want to get rid of the domains, or do you simply want a non-zero value for one of the order parameter components, right? Because as you can see here in these pictures, right here, right? Clearly there are domains here, right?
Right, right.
So domains have not been destroyed, even though we have a finite value of delta J. Nonetheless, this system will order at a finite temperature.
So, and you're saying that these would be
And
the
of course,
same as in the random field Ising
But
model?
in the random field Ising model, you cannot ask that question because you don't have that second degree of freedom
Right.
that undergoes a transition here.
Oh,
So there is no equivalent to that statement.
So I see. So if I
Right.
separate into the Ising degrees of freedom for the random field to say that's the same, but now I have a
Right,
different
right,
Ising.
exactly. Then
Okay.
we have the magnetic degrees of freedom here, which are not the magnetic degrees of freedom
Got
in the
it.
random field Ising model because those represent the stripes here, right?
Got it.
More questions?
As you said, there is an interesting thing going on in the middle, in the supposedly spin glass.
Right.
I would like to some comments of you. I don't know if the lower critical dimension of the spin glass transition is settled. So, what kind of a spin glass do you really expect in that domain?
Yeah, actually, I cannot really answer these questions. And we certainly have not looked at this problem. The only things that are clear is that there should not be a direct transition between the two phases because according to Lambda it should be first order, but according to Imre Ma, first order transition cannot exist in 2 dimensions in the presence of this order, right? So therefore, there's only 2 simple possibilities left. One is that the paramagnetic phase extends all the way down to 0, right? And the other is an intermediate phase. In earlier work, there has been some indications that there might be spin glass order down here, but we have not looked at that parameter region. It should, yes. It may be just a finite range order, right? So again, we have not looked at this. Other people have reported that something like this might be there.
More questions? I see none at this point, so let's thank the speaker again.